Good afternoon. I want to welcome everyone to our Badger Dairy Insight webinar series. The title of this one is Honing Our Measures of Feed Efficiency. The Badger Dairy Insight series is sponsored by the University of Wisconsin-Madison Division of Extension Dairy Educators. Today we have three speakers talking to us, and our first one is Dr. Francisco Penagaricano, who is the assistant professor at the Department of Animal and Dairy Sciences for the University of Wisconsin-Madison. He is broadly interested in quantitative genomics and computational biology. His research program focuses on developing and applying methods to dissect the genetic basis of economically relevant traits in dairy cattle. His research involves gene mapping, genomic prediction, multi-omics data integration, and network modeling. At this time, I'm going to pass it over to Dr. Francisco. And if you have questions, please feel free to put them in the chat box, and we will either take them as the presentation is going or at the end.
Thank you, Jackie, for the introduction, and thank you for the invitation. It's a pleasure to be here today. So we will be talking about feed efficiency. Let me start with that quite important question. What's the importance of feed efficiency? Well, feed represents more than 50% of the total production cost. And if you think about it, the benefits of improving feed efficiency are multiple, including increased farm profitability and reduce the environmental impact of dairy farming. Because if we can produce the same amount of milk with less feed, then we will need less land, probably we will produce less manure, and probably we will reduce greenhouse gas emissions. So I have one slide about the basics of feed efficiency using an energy flow in a cow. So we have the gross energy of feed, and some of that energy is lost as feces, gas, and urine and heat for digesting and metabolizing feed. And then at the end, some of the energy is captured as milk or body tissue. And in that process, of course, some energy is lost as heat for maintenance. So if you think about it, how can we improve gross feed efficiency? Well, there are two ways. We can improve here the conversion of gross energy into net energy, or we can improve here, basically increase milk production relative to maintenance. So I have here a successful story that is the change in milk yield in the last 60 years. I'm here plotting the amount of milk production per cow per lactation in the United States in the last 60 years. And as you can see here clearly, there has been a tremendous improvement in milk production per cow per lactation. In fact, a cow today, she produces more than twice as much milk as a cow 60 years ago. And of course, greater productivity increases feed efficiency because higher production dilutes out the proportion of feed used for maintenance. And genetic selection for milk yield has increased feed efficiency indirectly through the dilution of maintenance. Now, the marginal benefits of increasing productivity on feed efficiency diminishes as milk production increases, and it varies. So we basically, if we want to keep improving feed efficiency, we need to target directly feed efficiency, and the way that we do it is using residual feed intake. It's a common way to measure feed efficiency in dairy cattle and also in beef cattle. And we measure the residual feed intake as the difference between what we observe in terms of intake and what we predict. I have here a bunch of cows. Imagine I can observe a daily intake, and I can somehow predict intake based on body weight and production. And you will see that I have some cows. This one, for example, she's eating basically 15 kilos of dry matter intake, but I would expect that she would eat roughly 20. So she's eating less than what I expect. She will have a negative residual feed intake. She will be a very efficient cow. At the same time, I will have a cow like this one. It's a cow that is eating roughly 24, 25 kilos of dry matter intake daily. But based on her production and her body weight, I would expect she would eat 18 kilos. So as you can see, she's eating more than what I expect. Residual feed intake is positive, so she is a less efficient cow. So the dairy cow feed efficiency effort started roughly 13 years ago and involved 4 land-grant universities, including the University of Wisconsin, Michigan State, Iowa State, and the University of Florida, and also the USDA. And this effort has been supported by federal funds and also industry funds. Nowadays, we have more than 8,000 lactating Holstein cows with feed efficiency records. So what we do, we measure feed intake daily, we measure milk production daily, we measure milk composition 4 times a week, and we measure body weight once or twice a week, or every 2 weeks. So we measure also other variables, including milk spectra. We are collecting body temperature. We have data about rumination, about activity, about line, and we have also some metabolites. How do we measure feed intake? We are measuring feed intake in 5 different research farms, and depending on the farm, we measure intake using these blue gates, or we measure feed intake using these Gallen gates, or even we measure feed intake in tie stalls. So we basically convert the feed intake into dry matter intake, and then using milk production and milk composition, we can calculate milk energy. We have body weight records, so with body weight, we can calculate metabolic body weight and the change in body weight. And we basically use this model, and this model has what we call the 3 energy sinks: milk energy, metabolic body weight, and delta body weight. Dry matter intake is the response variable. We basically calculate residual feed intake as the difference between what we observe in terms of dry matter intake and what we predict using this linear regression. Now, a very important question is, okay, what's the variability? What's the genetic variability of feed efficiency? As you can see here, I have different traits: milk energy, metabolic body weight, dry matter intake, and residual feed intake. Remember, we are measuring residual feed intake as our measure of feed efficiency. And as you can see here, it's a quite heritable trait with a heritability of 16%. I'm bringing this table. This table has many of the traits under selection. And as you can see here, I have the heritability of the traits in the diagonal. The most heritable trait is body weight composite with a heritability of 0.40. Then production traits have a heritability of 0.2. And then I have basically longevity with heritabilities around 10%, fertility with heritabilities around 2, 3, 4%, and health with low heritability. So in other words, feed efficiency is more heritable than most fertility, health, and longevity traits. Feed efficiency has a heritability of 16%. That's great news. We decided to use feed safe as the trait in the national evaluation. This trait was developed in December 2020, so 2 years ago, and feed safes combine residual feed intake and body weight composite. Here I'm showing the distribution of PTA values for feed safe in the Holstein population, and you can see that we have a beautiful distribution. Feed safe is measured as pounds of feed safe per lactation, so larger positive values are more favorable. And as you can see here, between the extremes, between the most efficient and the least efficient cows, we have roughly 450, 500 pounds less of feed in lactation. Now, probably an important question is how consistent is residual feed intake within a lactation, and for that I will be showing data from 400 cows from the University of Florida, where we have roughly 14,000 daily records of feed intake. So we measure these 400 cows in what we call early lactation, the 1st to the 5th week postpartum. As you can see here, we have observed dry matter intake, and we have the predicted dry matter intake based on milk energy, metabolic body weight, and change in body weight. And then for the same group of cows, we measure intake in milk lactation between the week 9 and 15 postpartum, again for the same 400 cows. And then we calculate the correlation in residual feed intake between milk lactation and early lactation. I have good news here. The correlation is high, almost 0.5 positive. That means that cows that are efficient in early lactation tend to be efficient also in milk lactation, and vice versa. There is some re-ranking, but it's small. So residual feed intake is, let's say, somehow stable in a lactation. What's about across lactations? This is a study that we performed last year. For this, we use roughly 60,000 weekly records of residual feed intake. We use data from 5 research farms from 2007 to 2021, and we have roughly 5,000 cows in first lactation, cows in second lactation, and cows in third lactation. And actually, we calculate the genetic correlation between first and second lactation. For that, we use the PTH of the sires. And as you can see here, the genetic correlation is 0.99, super correlated residual feed intake in first lactation with residual feed intake in second lactation. We did the same between second lactation and third lactation, very high correlation, 0.98. And the third one, we calculate the correlation between first lactation and third lactation. The correlation is lower, it's around 0.80, but also we have a problem with the structure of the data because we do not have many cows with residual feed intake records in first lactation, and again, the same cow in third lactation. So what about feed deficiency and health disorders? This is a question that we usually receive. What about the relationship between efficiency and health disorders? I'm showing this data. This is from the University of Florida. The same study that I showed you before that we published a year and a half ago. For this data, we have almost 400 cows. We classify the cows between very efficient cows, this in the first quartile, to less efficient cows in the fourth quartile, right? We have roughly 100 cows in each group. And then we evaluate the incidence of health disorders in the first 90 days postpartum, including retained placenta, metritis, mastitis, DA, lameness, even pneumonia, multiple disorders, and even if the cow left the herd by 30 days. And as you can see here, just go directly and check the last column. I have the p-value of the statistical test. There is no association between efficiency measured in milk lactation, and the incidence of health disorders. Great news, again, if we select and we improve feed efficiency, we will not have a negative impact on health of the cows. I wanted to bring another data set. This is from the University of Wisconsin-Madison, was published also 1.5 years ago. We have here almost 200 cows. The cows were classified between healthy cows, no health disorders, one event postpartum, more than one event, and then we try to associate the health status with different traits, including, as you can see here, residual feed intake, or even energy corrected milk divided by dry methane intake. And as you can see here, no association again between feed efficiency and health. Very good news. If we select for more efficient cows, we will not have any negative impact on health. So this is probably the million-dollar question. Why some cows are more efficient than others? In other words, why some cows need less feed than others of similar body weight and milk production? I don't have the answer. Now, some processes that probably contribute to feed efficiency are feeding behavior, diet digestibility, the rumen microbiome, the metabolism, maybe the physical activity, the thermoregulation. So one way that we, the geneticists, have to actually disentangle a trait is to perform a genomic scan. It's basically we scan the entire genome of an animal to try to find gene regions of genes that are associated with the trait. This is a genomic scan that uses basically 5,000 cows and roughly 60,000 SNPs across the genome. And as you can see here, the author performed this scan for primiparous cows and also for multiparous cows. And it's easy to see that there are very few genomic regions across the genome that are somehow associated with feed efficiency. In other words, feed efficiency, as we expect, is a very complex trait, very polygenic. Many genes are involved in this trait, and most of the genes have a small effect. It's interesting that in this peak here, in primiparous cows, this region harbors this gene, a beta-3 adrenergic receptor, and this gene is involved in energy homeostasis. And a very nice peak here in chromosome 4 in multiparous, this region harbors leptin, and this hormone is involved in regulating appetite. So two nice candidate genes. If you go beyond single genes and you think more about gene networks or gene pathways, the results are very cool. And this paper showed that some of these pathways that are implicated in dairy cow feed efficiency are related with biosynthesis of amino acids, with the metabolism of the proteins, with the digestion of carbohydrates, with the muscle development, with immunity, with the activity of the bacteria in the rumen, and with the mitochondria. Now, regarding the mitochondria, there are some very cool research in beef cattle comparing very efficient animals versus less efficient animals. In other words, animals with low residual feed intake, very efficient, versus animals with high residual feed intake, less efficient. And research has shown that the efficient animals have greater mitochondrial density. They have greater mitochondrial function. They have greater antioxidant capacity and have lower oxidative stress. And this probably suggests that the differences in the mitochondria and the mitochondria function actually explain part of the difference that we observe at the level of feed efficiency. Now, coming back again to this million-dollar question, one of the processes that we believe can explain feed efficiency is feeding behavior. And we have been working on that. Here in UW-Madison, we measure feed intake using these blue gates. And with these blue gates, we can get a lot of information regarding the feeding behavior of the animals, including number of visits per day, the duration of actually each visit, the intake in each visit, and of course we can calculate feeding rate. And for this analysis, we use basically almost 80,000 records from 1,300 cows here at the UW-Madison. This is data from 2009 to 2020. And we calculate both the heritability of the trait, so basically the proportion in the phenotypic variance that is explained by additive genetic effects, and the repeatability that basically measured the correlation. And as you can see here, we evaluate a bunch of different feeding behavior traits, including number of visits, duration of the visits, total duration in a day, intake per visit, and the feeding rate. And the very interesting thing is that feeding behavior traits are heritable traits with heritabilities between 0.09, 0.10 to 0.23. And they are also repeatable traits with correlations that go between 0.30 and 0.50. We also calculate the genetic correlations, how are genetically correlated. And as you can see here, some of these traits, as you expect, are highly correlated. For example, number of visits and duration of each visit, they are negative correlated, as you expect. More visit, less time in each visit. But I think the most important thing is, okay, we are measuring different feeding behavior trait. Is it a good indicator of feed efficiency? In other words, can we use feeding behavior as an indicator trait of feed efficiency? And for that, what we did is to calculate the genetic correlations between feeding behavior traits and feed efficiency, including residual feed intake. And we got very cool result. As you can see here, feeding rate per visit, it's highly correlated, genetically correlated with residual feed intake, both if we measure feeding rate per visit, or we, instead of define visit, we define a meal. And also intake per meal is highly correlated with residual feed intake. Very interesting results. Let me give you some take-home messages here. Feed efficiency is an economically relevant trait. Residual feed intake is a heritable trait with a heritability around 15%. Genetic selection can effectively improve dairy cow feed efficiency. Now, residual feed intake is repeatable within lactation. I show you data. Residual feed intake is highly correlated across lactations. I show you data. And residual feed intake of feed efficiency is uncorrelated with health. Now, residual feed intake is highly polygenic. There are many genes affecting this trait, many genes with small effects. And there are some important mechanisms that can explain the differences in feed efficiency between animals, including differences in metabolism, differences in the rumen microbiome, in the activity of the bacteria in the rumen, and also the mitochondrial function. And our most recent data has shown that the feeding behavior traits are heritable and repeatable. Feeding behavior traits are genetically correlated with feed efficiency traits. And some of these feeding behavior traits, like feeding rate, could be used as indicator of dairy cow feed efficiency. With that, again, thanks for your attention. Thank you for the invitation. And of course, I'm open for questions.
So we have a question. What is the correlation of lactation RFI and efficiency in replacement animals?
That's a great question. So basically, what's the genetic correlation between efficiency in the lactation stage versus efficiency in the growing stage? And We do not have much data to answer that question, but the preliminary data that we have suggests that that correlation is positive, but it's quite low. So basically, to be efficient in the growing stage and to be efficient during lactation are basically two different traits.
Perfect. And I think too, you know, being as feed efficient with our animals as we can, especially as milk prices maybe come off a high, we really need to look at our bottom dollar and what we can do to get some more dollars in our pockets. Francisco, do you want to answer the question? If we include RFI as a small component in a selection index with many traits, will we actually improve RFI very much?
That's a great question. And let me say that first, we always recommend to use economic selection indices to identify and select animals instead of using individual traits. So my first answer is yes, we have to use a selection index. The selection indices that we have, like a net merit and cheese merit, they have a 13% weight in feed efficiency. If we combine residual feed intake and body weight composite, 13%. And I would say that amount of weight is due to the heritability of the traits, correlation, and economic weights. And the answer is yes, we will improve feed efficiency. Remember that genetic selection, contrary to improvement in nutrition, in management, or in cow comfort, the changes achieved through genetic selection are incremental, accumulative, and permanent, and that makes genetic selection a very cost-effective strategy. So my answer is yes, we need to use economic selection indices. The weight it's not too high, but it's 13%. That's good. And we will improve efficiency through genetic selection.